So lecture number 3, last week we introduced models, and I realized for anybody who hasn't done any model theory or is even familiar with the idea of a model, it may not be something that comes very quickly. So I did want to take some time to go over exactly what a model is again and give some examples of theories and models. And then hopefully after we kind of talk about models in detail, we'll be able to go into some actual model theory and then talk about how we embed models into other models, some really powerful theorems, what we can learn about different theories by examining their models. Awesome, and then what it means for models to be isomorphic or to satisfy the exact same sentences. So cool. So really just a quick recap. A structure is a set equipped with functions, relations, and constants. And a sentence is a logical formula with no free variables. So, okay. This one is called density, or like the property of being dense. This one is like the function f has no fixed points. So basically any idea that you've come across in mathematics, like a statement like, oh, like this function is continuous, or the Pythagorean theorem. Any theorem or postulate or conjecture that you can come up with has an analog as a sentence, a logical formula with no free variables that can accurately express exactly what that theorem says. Sometimes the sentences can be really, really, really long. And I know not everybody is familiar with this sentence with quantifiers notation. So I kind of just wanted to acknowledge that. And then also, as we dive deeper into model theory, things are going to become more and more complex with notation. So this is kind of where the learning curve, I would say, for logic has become really, really steep. So, of course, take time to ask questions. And it's hard to remember exactly what all the notation means. So don't feel bad about like taking time to look back in your notes and familiarize yourself with all the syntax and all the symbols. Because if you don't remember those, or if you come across a theorem or a definition that makes use of those, you're going to get really lost really fast. And that's the unfortunate thing. I think that it becomes a lot easier when you work with these things a lot, especially when you do a lot of exercises. So I've actually been thinking about assigning exercises in case that might help people kind of grapple with all the different syntax, because you really need to get your hands dirty and work with these things. For those of you who have that already, that's fantastic. But for those of you who haven't, I do think that actually working with exercises will make a really big difference in terms of your understanding. Okay. Moving on, so we've defined what a structure is. A structure models, or is a model of a sentence, if the sentence is true in that structure. And by true, we mean when we use a delta assignment for that structure, we get out true. We have a way of finding out if a model satisfies, or if a sentence is valid in a structure. And we went over that last lecture in a lot more depth. So moving on for right now, so some examples of the models, the ones that I've talked about. So here's, again, so the model is the kind of fancy symbol, and there's also the set underneath, and it's important to distinguish between those two. So in these two examples, I have the structure Z with the order and Q with the order, the integers and the rationals. I know last lecture I kind of added, for at least for this structure, I had, I had like addition, multiplication, the constants, the order, and that's fine and all. And I definitely included all of those to show like you can have all of these things. You can add all of these functions in if you want, these relations and constants. But for now, actually, we're going to kind of work, oops. For the example that I'm going to give for these two being a model for a sentence, we're going to kind of work minimally. We're only going to use the functions, relations, and constants we need, hopefully to kind of lift some confusion. So that's kind of why my examples have gone from, with a lot of functions, constants, relations, to very, very few. So here's an example of two structures. They both have these underlying sets, integers and the rationals. And they both have the inequality relation, less than. And then coming up with an example phi of a sentence, let's say phi is exactly this one. So for all x, for all y, there exists z, x is less than z is less than y. So what happened? Okay, fantastic. So in this case, the structure Z is not a model for phi. That's what this symbol means. Not models, not model, not a model of, or does not model. So in this case, Z is not a model for phi. It's not true that anytime we have 2 points, that we can find a third point in between them. And it's true in Q. It's true in our structure with the rationals and with inequality, because anytime you have just 2 fractions, you can always find a third fraction in between them. Okay, so that was just a really quick recap of what it means for a structure to model something. A structure models, or is a model of a theory, if it models all the sentences of a theory. And remember that a theory is just a collection of sentences. So now that we've kind of gone over a really quick recap, we're going to actually go through some examples of different theories. So the 4 that I'm going to go through are groups, equivalence relations, irreflexive graphs, and piano arithmetic. So first, the theory of groups. Now, I'm not totally sure who has done a little bit of group theory, who's even done like some abstract algebra. So for those of you who haven't, I'm sorry that I'm not going to be spending a lot of time on it, but really quick, a group is a set equipped with a binary operation such that the following are true. Question in the chat. Are we stipulating at this point that structures are sets? Terminology could get confusing once we get into set theory or try to do philosophy, but this may not be an issue at the moment. Ooh.
What?
Hi. So somebody just asked a question in the chat. I think that for now we'll stick with a structure is a set equipped with these things. You could say a structure, I guess, is a collection of some underlying universe, often in our case, a set equipped with functions, relations, and constants. So there is a tiny bit of a distinction there. I think for now, we're going to just stick with them being sets with functions, relations, and constants. Thank you, though, for pointing out that that's not always the case. And we're kind of using a simpler definition here that in the future, as we get more in depth into the subject, that we will have to go back and revisit. Cool, so thank you for pointing that out. So again, those who aren't familiar, a set equipped with a binary operation such that the following are true. Let's say the binary operation, I'm going to use the same one up there, is dot, so x dot y. This is our binary operation. And there's a specific constant e. So there's 3 requirements. E is the identity element. So there is an identity element. Each point has an inverse. And associativity of the binary operation. So written, like in actual sentences, this is what we're looking at. So for all x, e dot x is x dot e is x. So this is e being the identity. Oh, I switched them. So for all x, for all y, for all z, we have that the binary operation is associative. That's not actually what I wrote. X dot y dot z. And for all x, there exists a y. X dot y is y dot x is e, actually. No, yeah, that's true. Fantastic. So, so some examples of groups and as an extension, some models of groups. So we'll take one of them to be z with addition. So just all the integers. This is an infinite group. 2, 1, 0, 2, 3, dot, dot, dot. 0 is the identity. It's the additive identity. We know that addition is associative, and every inverse is just the, if your number is positive, it's the negative version of that number. If your number is negative, it's a positive version of that number. And then second example is, let's do z2, 0, 1, 2 with addition mod 3. So this is 0 mod 3 is basically any integer that's divisible by 3. 0 is our identity. 1 and 2 both have inverses each other. So if I add 1 and 2, I get 0 mod 3. And if I add 2 and 1, I also get 0 mod 3. And this, just like regular addition, is also associative. So I have these 2 different structures. Again, both of them sets, both of them have a function. And in this case, they're both groups because they satisfy these 3 statements. So this is how we could say, I'm going to call this TH sub G for the theory of groups. And again, it's just the union of these 3 sentences, the collection of these 3 sentences. Z with addition models THG. So Z with addition is a model of the theory of groups. If there are questions on groups, I think that we can definitely answer those in the chat. Again, in terms of thinking about offering exercises, I think that I will offer some on groups for people who aren't as familiar. But for now, moving forward, talking about the theory of irreflexive graphs. So really quick, a graph. A graph is a collection of vertices and edges. So basically, I'm going to use little stars. Vertices, little points, and edges, lines between them. Now by irreflexive graphs, we mean that there is no edge from a point to itself. And I've only included irreflexive. Oh, and this relation here is there is an edge between two vertices. They've only included irreflexive so we could see these two axioms. So these edges, so Leah asked, are these edges directional? And in this case, no. So actually I did kind of draw an arrow, the first one, and that was a mistake. So in this case, these edges are undirected. So technically I could say irreflexive undirected graphs. But you can have, absolutely, you can have directed graphs in which all of the edges do have a direction. And that's super useful when talking about graph theory. This is, again, something I'm thinking about assigning exercises on because graphs are just a really neat thing in general, really useful. And I just like graphs. Okay, so our graphs here are undirected. For all x, it's not the case that Rxx. So for every vertex, it's not the case that there's an edge from the vertex to itself. And this is I guess a statement about not being directed, is that if there's an edge between x and y, there's an edge between y and x. So this graph right here is a model of the theory of irreflexive graphs. So anytime I have a graph that's irreflexive, that's undirected, it's a model of this guy. Now, if I add direction to this graph, I don't satisfy this sentence, and therefore this is no longer a model of the theory of irreflexive graphs. Similarly, if I add an edge from a vertex to itself, I'm not satisfying this sentence, and then again, this is no longer a model of the theory of graphs. So, or the theory of irreflexive graphs. So the point that I'm really trying to drive home here is that a model of something is a structure in which all of the sentences of the theory are true. So let's look at our third example is the theory of equivalence relations, where this kind of curly E is going to be, is equivalent to. Now, equivalence you can define in a lot of different ways. Some you can say, I mean, equality is an equivalence relation. An example belongs to the same partition, and you could define partition as you like. Is isomorphic to. There exists a morphism between. Kind of any kind of equivalence that you could think of. So the theory of equivalence relation is three statements: reflexivity, symmetry, and transitivity. So it's the case that x is always equivalent to itself. If x is equivalent to y, y is equivalent to x. And transitivity, which basically A equals B, B equals C, therefore A equals C. Any equivalence relation that you can think of, including just regular equality over the numbers. So if I had a structure, let's say, I'm going to use the real numbers and just equality. This is my structure. This is my relation. This is a model of the theory of equivalence relations. And then lastly, the kind of most complex example that I'm going to go through is the theory of piano arithmetic. So for all three of these examples, I've been able to explicitly give you a model of its theory. I've been able to actually write down and explain this is exactly what a model looks like. And that's not the case in piano arithmetic. So piano arithmetic has, we have addition, multiplication, the successor function, and the constant 0. So really quick, the successor function is a unary function, and it just takes in any number x, and it gives you x plus 1. So the successor function is the way that we formalize the idea of this is the next number. So I've written down what I can of the theory of piano arithmetic. So really quickly, kind of these 6 first ones, for all x, s of x is not equal to itself. If x is not 0, then it has a number, it has a predecessor. 0 is indeed the identity. X plus s of y is s of x plus y. We have the zero product property, and kind of also how multiplication works. These are the 6 sentences that I can write down quite simply, and then we have an axiom schema. We have an axiom for each possible sentence. So breaking this down a little bit, by phi of x, y bar, what I mean here is phi is a sentence with x as a, well, not a sentence. Phi is a formula with x as a free variable. And y bar is equal to some collection, some finite collection, y1, y2, dot, 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 yn, where this is a collection of parameters. So I could have easily just written phi of x and just said phi is some formula with x as a free variable, if I didn't even want to include extra parameters, extra things that I plug in to my formula to evaluate if it's true or not. So I could have just said phi of x, but we want to kind of talk about all of the possible formulas in the most generality, which is why we include, we say, it doesn't actually matter any formula that takes any number of parameters. Maybe phi is some kind of function, or in the formula phi, it has some kind of function that takes n parameters. So when we're evaluating, or when we're trying to represent phi of xy, we're saying phi takes some free variable x, and it also has a function y that takes in y1, y2, dot, 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 yn. So this notation is confusing. For now, kind of just imagine phi of xy is the most general way that we can write any formula. So for each phi of xy, we have, this is called the induction schema. So long list of symbols here. For any collection of parameters that you can plug in, if it's true, if phi is true when you plug in 0, and it's the case that if you plug in x, it's true for x plus 1, then phi is true for all numbers. This is just induction. This is the principle of induction. Induction being a tool that people use all the time to prove something about the numbers. There's many different, I think there's an entire book. My friend has an entire book on different kinds of induction, which is just crazy. But the case that people are most familiar with is you start with the 0th, or sometimes the first case of something, and you say this is your base case. You prove that something's true for the base case, and you prove that if it's true for n, true for the nth case, that implies it's true for the n plus 1th case. N plus first plus 1 first case. Again, not going to go a whole lot of detail into induction, but basically if you can prove that it works for every next number, then it works for all the numbers. So again, what I've given you are examples of models for these 3 other examples, but I unfortunately can't do that for piano arithmetic. Now, part of the reason is, well, not part of the reason. One difficulty in coming up with a theory for piano arithmetic is that for this one, theory of equivalence relations, irreflexive graphs, and for groups, these are all what we call finitely axiomatizable. By finitely axiomatizable, I mean that I can write down their sentences. There's only finitely many sentences in their theory. And that's not the case for piano arithmetic, because this induction schema here is an axiom for each possible sentence. There are infinitely many sentences. Now, there's a sub-theory here called P0. And P0 is just these first 6 statements without the principle of induction. So what I could say is if I wrote PA, and I define this as the theory of piano arithmetic, and if I wrote P0, I shouldn't use the abbreviation in the definition. Piano arithmetic. And P0 is PA without induction. What I can then write is PO is contained in PA. And then it would be the case that anytime I had a model of piano arithmetic, I would also have a model of P0, P naught. So P naught, because it's this collection of only 6, it is finitely axiomatizable. But then when we suddenly include this induction schema, which is infinite, we no longer have a finitely axiomatizable theory. We have an axiomatizable theory, but not a finite one. And we sure do hope that, so I think Julia is still here. Julia told me a story once. Weren't you in a class and you asked if piano was consistent?
Ooh, did I ask if piano is consistent? Yeah, something like that. But yeah, basically, like, yeah, I asked Sedki. I was like, wait, but is piano consistent? It's like, oh well, goodness, we hope so, because otherwise, none of the arithmetic we're doing is correct or holds water. So, but yes, I did ask that. Scary.
I mean, that's a reasonable question to ask. By consistent, because I maybe defined that last lecture, but I haven't defined in this one. By consistent, we mean has a model. So asking, wait, does piano arithmetic have a model? And it's like, well, we sure hope so. We sure hope that there isn't a contradiction in all the arithmetic that we're doing. So there are, well, I have an entire book called Models of Piano Arithmetic. So the question of the consistency of piano arithmetic and what the models of piano arithmetic look like. There's like a bizarre, this is one of those interesting kind of edge philosophical things where it's like, well, what about just the natural numbers with addition and multiplication? Sung, maybe at this point we want to distinguish between consistent, no contradictions, and satisfiable has a model. Don't know if you've covered the completeness theorems yet. I have actually not covered the completeness theorems yet.
Consistency means you have a model, though, right?
Right.
Yeah.
The point that I wanted to make is that in first order logic, those are equivalent, but in other logics, they are not necessarily. So I'm not sure how important this is for now because we're doing model theory.
Nice.
Is that Song?
Yeah. Hi.
Hi, Song.
Hi, Julia.
Oh my gosh. Sorry. But
Song,
oh my gosh, hi. Oh,
hi.
I was like, what's that beautiful voice?
Sung, Julia, and I took logic classes together at Berkeley, and we've been through a lot together. I could put it that way.
I'm going to mute, not derail this further.
Oh, okay. Well, thank you, Sung, for distinguishing. I actually didn't know that in different, in first order logic, well, I did know that in first order logic that being consistent and being satisfiable are the same thing. So again, not having a contradiction, having a model. But apparently in other logics, that's not the case. So I will have to read up on that. Okay. So piano arithmetic, we could say, what about just the natural numbers with addition, multiplication, successor function, and 0? Like, is this not true? Is piano arithmetic not true in the natural numbers? I mean, we use induction all the time to prove properties about the numbers. And certainly we can prove P0 has models. There's, again, we hope that's true, but we don't actually have a proof that the induction schema is true for each possible phi. So again, there's this like really interesting philosophical set theoretic, model theoretic like question or like distinction here that I unfortunately don't have time to go into. And to be honest, I don't completely understand it myself, or I do after I study for model theory a lot more, but piano arithmetic is crazy. So here are some 4 theories I've given you for some of them examples of models or explanations why examples of models aren't that simple to give. So I think that for now, I'm going to assume that we understand what a theory is, what a model is, what a sentence is. And if that's not the case, then certainly ask questions in the Discord and we can talk more if you're kind of struggling with the idea of a model. Fantastic. So going over some important concepts. Is it important for this class to fully understand piano arithmetic? Not yet. Again, I don't totally have my head around piano arithmetic. Yeah. So no. If you have questions like what do models of these look like? Well, that's a great question, and I will refer you to Kay's book, Models of Piano Arithmetic. But for now, it's enough to understand that this is a theory, that it's axiomatizable, but not finitely axiomatizable, and that the models of it are bizarre and elusive. Okay. With T be an L theory and phi an L sentence. So really quickly, what do I mean by an L sentence and an L theory? So by L sentence, I mean a sentence in the language L. And by theory, I mean a theory in the language, with the language, under the language. Under the language L. The difference between an L theory and just a regular theory is that for an L theory, you're specifying, you're kind of saying it's a theory over a specific language. So what I've written here is for the theory of groups and for the theory of graphs, the languages are different, because in the theory of irreflexive graphs, I only have one relation, but in the theory of groups, I have no relations. I just have a function and I have a constant. So if I were to say a sentence in the theory of groups, I would say an LG sentence. Now, the importance of distinguishing between an L sentence and an L theory is only to say that T is a theory, phi is a sentence, and that they operate over the same language. It wouldn't make as much sense, or wouldn't really make any sense for me to ask the theory of irreflexive graphs, is there an identity element? Is there an identity element under the binary operation? So is it true for all x there exists an E such that x star E is equal to x? And if I ask that question for the theory of irreflexive graphs, the theory of irreflexive graphs is not going to understand what to do with that, because I haven't actually defined in this language what this binary operation is. So an L theory and L sentence is no different than any other sentence or theory, but I'm just specifying that they're over the same language. I hope that's clear. Phi is a logical consequence of T if, for all models, if M is a model of T, then it's a model of phi. So this is a way of saying, here's an example. It's for the theory of groups. The theory of groups technically only contains these 3 sentences, but a consequence of the theory of groups, let's say for all x, if x equals E, that implies, or no, if for all y, x star y equals y star x equals x, this implies that y equals e. So what this is saying in just English is the identity is unique. You cannot have another identity element that is not equal to your original. That is the case in what's called a groupoid. So there is such a structure in which that is true, but not for the theory of groups. So this sentence, while it's not listed in the original theory, if you assume these sentences, this is a consequence. This follows. You can start with these three and use some deduction rules to eventually get to phi. So when I say logical consequence, it's basically exactly what you think. It's something that logically follows from the assumption of several different sentences. And in terms of models, anytime you have a model of a theory, you have a model of that logical consequence. In which case we'll write that T models phi. So there's a difference between a model modeling a sentence versus a theory modeling a sentence. So in this case, it's phi is true in M, curly M. And in this case, it's phi is a logical consequence. Okay, so next definition, a theory is consistent / satisfiable if it has a model, and is inconsistent if there exists a sentence such that phi is a logical consequence of the theory and not phi is a logical consequence of the theory. So thank you, Sung, for pointing out that. So I wrote consistent / satisfiable if it has a model, and that's only true that those are the same thing in first order logic. Oh, man, Sung, if you could send me some examples of different kinds of logic in which that's not true, because I'd really love to read up on that. Okay, so when we say consistent, we mean has a model. So moving forward, a theory is complete if for every sentence phi in its language, T is a model of phi, or T is a model, or no, not model. Phi is a logical consequence of T, or not phi is a logical consequence of T. So really quick, there's a bit of a distinction. T is a model of phi. T is not a model of phi. This is not the same thing. I guess I should say. These two are not the same thing. There's a difference between not modeling a sentence and modeling the negation of a sentence. Man, I should have prepared some examples of that, but it's kind of like, ooh, but then you could talk about the law of excluded middle. Okay, anyway.
You can be red, you can be not red, and then you can be green. Like, so being not red is not always the same as being green, maybe. Is that a good example?
Wait. Yes. I think that the only thing is that with negation of phi, you could say that the only two options are being red and green.
Yeah.
So if you're
those
not
are my
red,
only options, but yeah, true.
Right. So if you're not red, then therefore you're green. But I think that your example is better because it's not phi, because there's this distinction here. It's not always the case. Like if phi is, man, an example I think of is it's very, very simple, and this equality is true. I think I'm going to stick with Julia's example. I think that one's the best.
Sorry, can I chime in?
Yeah.
So I think what may be the problem is that, like, you're thinking of models satisfying formulas. If it's a theory that's not necessarily complete, then if the theory does not prove phi, it does not mean that it proves not phi.
Oh, yes.
Is that the sort of thing?
Yes. Totally,
Yeah, okay.
totally the case. So there's a difference between phi is not a logical consequence of a theory versus not phi is a logical consequence. Thank you, Sun. That's precisely it. So there's a difference between a sentence phi being there's no way that we can prove this sentence phi given the sentences in the theory that we have, versus actually the negation of phi, we do have a proof of that. We can actually deduce that from the sentences of T. Awesome. So theory is complete if for either phi or not phi, it's a logical consequence of T. And that's very, very useful because that means that our theory, I would say, is strong or is powerful or it knows a lot. Like every sentence phi in the language, T has an opinion about. It has a definitive, this is true or this is false, and I can prove it. So a theorem is the compactness theorem. So any set of sentences, aka a theory, has a model, if and only if every finite subset of it has a model. So there are proofs of the compactness theorem. And in terms of, I think somebody last lecture asked about proving that there does not exist such a sentence, or proving that if there does not exist such a sentence, that it implies that there's a model. I think that's a model existence theorem. There's a question about like, okay, so consistent theories have models, and you can use that to get to completeness. And there's also some like maximal consistency lemma, the Lindenbaum lemma. I think there's like syntactically, if you could build models, I think that I might do like a side video on these and a side video about the complete compactness theorem, because these things are very interesting and very powerful, but they're quite technical. So I think that sometimes if something gets, I mean, we're already going into things that are really, really technical, but I think that if something gets like very highly technical, I might save that for a separate video and just upload it. That way people who are interested can learn about it. But if it's kind of totally over your head, then for the purposes of the lecture series, then we can move forward. Okay, so compactness is a tool often used to prove that something has a model, especially if it's not finitely axiomatizable, but you can still break up a theory into different finite chunks and prove that each of those separately have a model. We crave completeness and consistency. It would be really, really great if we could prove that theories that are really powerful, the theories that we use all the time, piano arithmetic and ZFC, to name two off the top of my head, if we could prove that those are both complete and consistent. We definitely run into some problems when we try to do that. So this is kind of the overview of models that we're going to stick to now. We're going to have to build up some more machinery in order to talk more in depth about completeness and consistency. And again, I'll do that separate video on syntactic completeness and the compactness theorem. But for now, we can now actually compare models of the same theory. So we can now talk about how different structures of a theory, or just different structures in general, are related to one another when they satisfy the same sentences, when you can prove one is embedded into another, and I'll explain what an embedding is. I think that I might, in that case, go through some examples of specific models and how they're related to one another. Okay, so I'm going to define my language. I'm going to write F for a function, R for relation, C for a constant. Because I'm going to be stating things about any language in general, I could write this like this, R1, Rn C1 Cn and say that, okay, there's finitely many functions, finitely many relations, finitely many constants. Actually, I should use different indices here because there's not necessarily the same amount. So this is J, this is K, and this is N. This is for kind of ease of what I'm going to define, which is already kind of heavy in notation. I'm going to say L is a language, and let F represent any of its functions, R represent any of its relations, and C represent any of its constants. So in that way, I get to talk about any language in complete generality. So here are two structures, curly script M and script N. M script is the model. Capital M is the underlying set. Underlying. Wow, it would be really nice if my pen worked. Okay. And the same thing for N. I have script N is the model, and I have just capital N is the structure underneath. So I've written here this kind of F, R's, and C's kind of with like a superscript. And what I mean by that is specifically for this one, this is the function F interpreted in the structure M. And this is the function F interpreted in the structure N. I'll try and enunciate so it's clear what I'm talking about, M or N. So I apologize if that gets confusing. Okay, and then this is the relation R interpreted in M and the relation R interpreted in N, because technically they're different things. Okay, so we have an L embedding, and again, the difference between an embedding and an L embedding is that the embedding is over a specific language. So I'm going to create this kind of function theta. This is a one-to-one map from the underlying set of M and the underlying set N that preserves the interpretation of all of the symbols of L. So what precisely do I mean by this? So if theta, if I take the function from M with some parameters, and I plug in those parameters where each of these is in the universe of M, if I put this through my function theta, this is exactly the same as doing the function in N and using what theta spits out of each of the individual points. Where the map, again, takes elements of M. So here's A1, A2, dot, dot, dot. And what I get out is theta of A1, theta of A2, yada, yada, yada. So you can think of this as like, here's my universe of M, here's my universe, here's my structure M, and here's my structure N. In either of these things, I have a function that if I examine, okay, here's the general function is f of xy. It takes in two parameters, just a specific example. And let's say in M, the structure is addition, or the function is addition, but at N, the function is multiplication. I don't think that this example is going to be true, but I'm trying to come up with two different functions that are both binary that you're familiar with. So in M, the sentence, I'm going to say 1 and 2 are the constants that I'm using. 1 plus 2 is a statement in M. And then if theta is the map that takes, let's say both of these are over the integers, then theta is a map that would take 1 and 2 also to the integers, but then the new relation, because this is over M and this one is over N, the new function, not relation, is multiplication. And in this case, this would not be an embedding.
because these are not the same thing. These are two. We haven't preserved. I guess we have preserved the interpretation, but relations would definitely not be true. So what we're talking about is maps between models over the same language, where every time that we interpret the symbols, we end up with the same results. So in the case of relations, a relation is true in M over with some specific inputs, if and only if after I map those inputs into N, the universe of N, the interpretation of R and N under their image is the same as the interpretation of R in M. And constants just get mapped to constants. So again, this L embedding is a way of saying the statements that I can make in M, functions, relation, and constants, is the way that they're used in M is also the way that they're used in N. Now, when I say they're used, that's not specific at all. But that's, I think, a good intuitive way of thinking about it. Okay, so that's an L embedding. A bijective L embedding is what's called an L isomorphism. I got a message. I guess it's not in the chat. Okay, a bijective L embedding is an L isomorphism. Again, difference between L isomorphism and isomorphism is that the L isomorphism is specifically over the language L. And this is a way of saying that these two models are isomorphic, because instead of just having a one-to-one map from M to N, if phi is a bijective L embedding, then I have that phi goes from M to N, and phi also goes from N to M, and is one-to-one in both cases, and in both cases preserves the interpretation of all the symbols of L. So there's a difference between two models, two structures, having an L isomorphism between them and being elementarily equivalent. So kind of the last thing that I'll define for today is elementary equivalence. Equivalence. So M and N are elementarily equivalent. If and only if for all, say 5x y bar L sentences. If M models 5x y bar, then necessarily N models 5x y bar, and the converse is true. If N models 5x y bar, then so does M. So this is, kind of put more simply, M and N model exactly the same sentences. So there's a difference here, because while two models may be elementarily equivalent, they're necessarily isomorphic. There's an L isomorphism between them. But just because you have an L isomorphism between two models does not necessarily mean that they're elementarily equivalent, because even though the interpretation of symbols of L, they're interpreted in the quote-unquote the same ways, that does not necessarily mean that everything that's true in one is true in the other. So I think next model theory lecture, what I'll go through more in depth are examples of L embeddings, examples of L isomorphisms, and examples of when two things are when two models are isomorphic and when they're not elementary equivalent. So again, elementary equivalence implies that there's an L isomorphism, but not the other way around. And I guess because I have 2 minutes, what I'm going to give a quick example of an L embedding is an inclusion map. From one model to another. So say, let's come up with an example. So M is even numbers, even integers. Even integers with addition and with the constant 0. And N is just all the integers with addition and with the constant 0. There's an inclusion map from M into N. And by that, I mean specifically the universe of M is contained in the universe of N. And the inclusion map, I guess if I wanted to write out for -2, 0, 2, 4, ... So here's the universe. Here's the universe for M and the universe for N. -3, -2, -1, 0, 1, 2, 3, ... What the inclusion map does is it says, okay, because each of these is contained in here, that is, this entire set is included in this one, I'm going to send each point of the underlying universe to itself in the larger universe. I guess I didn't write -4. So what this map does is it is indeed one-to-one. It's not onto, because the odd numbers get missed. But the interpretation of the constant and the interpretation of the function are still exactly preserved. So if I have the statement 2 + 4 in M, this is the same as the statement 2 + 4 in N. Now both of these result into the same thing. So inclusion maps, if you can create an inclusion map between two models, are L embeddings. An example of kind of the simplest, well, very simple L embedding. Now, L embeddings can happen even when you're not over the same universe. And those are obviously more complex, but hopefully kind of this example is like, okay, here's a one-to-one map in which the interpretations for the functions and the constants are exactly the same, and you can kind of see exactly how this is mapped. Like here's an explicit map from one universe to the other. And then you can see how, okay, a bijective L embedding requires the other way. So this is not a bijective L embedding, because I definitely don't have, what happens when we have L embeddings from N to M and from M to N? That's exactly what a bijective L embedding is. It's an L embedding this way, and that's an L isomorphism. And that's the kind of the model theory analogy between just having an injective, surjective, and bijective function. Or well, they are injective, surjective, and bijective all respectively, but then the added requirement that we have for models is that the interpretation of symbols is still the same. So it looks like we're just a little bit after 10 here. So unless there are, did not mean to erase that. Unless there are specific questions we'd like to go through before we call it a day, I think we'll go ahead and wrap up so I can have some coffee and make some monkey bread, which I found a recipe I'm really, really excited about. So just a moment. Any questions? No? Of course, anybody is welcome to ask questions in the Discord if they come up later. I think also Yazgar said that he was trying to upload some notes that he's taken, and that'll be really, really helpful. So thank you for that. Thank you everybody for coming.